Yes, now it's working. So we have the limit as x minus the square root of x as x approaches infinity. What do we have to do first? We're asked to find this limit.
You'll plug in infinity.
Good, good. Where is this going?
Infinity.
Good. Where is this going?
Negative infinity.
Excellent. So number 1, 0 over 0. Number 2, infinity over infinity. Number 3, infinity minus infinity. These are the first 3 indeterminate cases. 4 more to go. Total of 7. No one knows what this is. Okay. Now, in this particular situation, I could say, and it's clear, which of these two goes faster to infinity. However, this is still an indeterminate case, but sometimes we can do an analysis, like in this particular case. So which of these two you think will be more powerful? I'm not saying, I could say with the degree, but really the square root is not a degree situation. It's not a polynomial. But which of these two is the most powerful, will go to infinity faster than the other one?
X.
Yes. So big minus small will still be big. Okay. Now, a similar situation, that's why I wanted to pick this first. A similar situation, like for example, 29, which is limit as t approaches infinity from the square root of 25t squared plus 2 minus 5t. This is a different situation. I'm asked to find this limit. Oops, I touched that. I hope it's okay. Where is this going as t approaches infinity?
Infinity.
Awesome. Where is this going as t approaches infinity?
Negative infinity.
Awesome. So this is the situation, but now I cannot tell. Here I was able to tell that this is definitely much smaller than this. So this eventually will take over. But here I cannot say that. So it's an indeterminate case. There is hope. This was an indeterminate case, but there was no hope at the end. But this is in the indeterminate case, there is hope. So we'll see, how do we address this situation? And we had the difference quotient on this, and we had limits before on this situation. So what do I do? What is my only chance here? Only. Anyone? Okay, I'll give you a hint. It's the only way.
Multiply by conjugate.
Excellent. So the square root of 25t squared plus 2 plus 5t, the square root of 25t squared plus 2 plus 5t. Because this is 1. All this fraction is 1. Multiplication of this quantity by 1, nothing happens. Absolutely nothing. If I have $10 in my pocket and I multiply by 1, I still have $10. Okay. Can anyone multiply the tops and tell us what to write? I have to copy the denominator, of course. I have no choice.
25t squared plus 2 minus 9t squared.
Please, please,
Is that
please.
correct?
Please, please.
Is that a 5? What is that?
Yes.
Okay, sorry. So that would be minus 25t squared.
Excellent. Of course, these two go away, luckily. Okay, am I still centered? I think I am. Good, so then we have limit as t approaches infinity from, did I copy that? Let me just, I don't know, I just picked the problem. So it's 25t squared plus 2 minus 5t squared, 5t. That's fine. Good. Okay, so it is what it is. So we square this and we got that, and minus 25t squared, these two go away. So the numerator is 2. And the denominator is the square root of 25t squared plus 2 plus 5t. So in this case, I don't have to factor anything. There's nothing to simplify. I'm going to ask you again, where is this going as t approaches infinity?
Infinity.
Yes. And 2 divided by infinity. Now we apply the limit and we can write the final answer.
0.
Excellent. So then y equals 0, horizontal asymptote. I have to write at infinity. It could be at both, but we only checked at infinity, although we have to write that because I had to use infinity. Yeah. Whenever we use the infinity, and we did to get infinity minus infinity, then I cannot conclude that is more than at infinity. Now, this is not a pure rational function. It's not even a rational function. So I cannot conclude. It's those functions I could immediately conclude at both ends, but it's not a rational function. Okay, I want to show one more example with e. So let's choose one with e, something like, yeah, we can do this one or this one, 37. Let's look at 37, and then let me know if we need more. As you've noticed, they're all different. Yes, I know somebody asked about L'Hopital rule, but this, as I said, comes into chapter 4, but we will not wait and we'll discuss it in chapter 3. And this is a rule that only is applicable for these two cases. No other case, unless we change them into those two. Don't bother with it right now. It's not the point. It's not the time. Okay, so we're asked to find this limit. What do we do first? Yes. So when x approaches infinity, which of these two, that's a silly question, is the most powerful? I know you're going to say, of course, it's e to the x. So plug in infinity and tell me where this is going.
Negative infinity.
Of course. And the denominator, where this is going?
Positive infinity.
Of course. So it's one of the 3 indeterminate cases that we've seen before. So in this particular case, we will factor out, I cannot say the degree, but we will factor out e to the x. Because I cannot say the degree, these are not polynomial functions. So what is left in the numerator?
1 over e to the x.
Yes, awesome. We have 2 terms. I have to have 2 terms here.
-1.
Good, good. And in the denominator?
1 over e to the x plus 2.
Awesome. Of course, that was my hope, to be able to get rid of the problem. And now, can anyone give us where this is going and where this is going as x approaches infinity?
0.
Yes, because it's 1 over huge. If this is negative, careful. If this is negative power, it's a different story, right? But e to the x, when x approaches infinity, approaches infinity. 1 over huge is 0. 1 over huge is 0. So now, only now, the limit operator. Now I drop it because I applied the limit, and I can write the final answer, which is
-1/2.
Very good. Which means y equals -1/2 is a horizontal asymptote, definitely at infinity only. We use that. So basically, that's all I wanted to say about limits at infinity. I do want to talk for a moment about one limit that we will talk about it again later on, but it's a very important limit because you're going to see it again. Let me think for a second if I want to show it to you. I want to show it to you now. It appears again in chapter 3. I'm just looking for a second and see if they show the graph in chapter 3. I forgot for a second if we look at it. I'm just looking for 1 second to see an trig, derivative trig. Yeah, so we don't have to do it now. It pops up again in chapter 3. So there is no secret. What I wanted to discuss is, but there is no need to do it now. The limit as x approaches 0 from sine x over x. So this is 1. We don't have to discuss it right now. Don't worry about it. But that's what I wanted to show a graph of this, because we cannot determine this at this point. So, but we don't have to worry about it. I'm going to have to potentially touch this because I need to plug in my device. So it doesn't, okay, good. So we don't have to worry about it at this point. But what I was going to show, and we will discuss it later, you will see that this function, it's a very important function. So it's sine x divided by x. And when we graph it, I'm just going to graph it only between -1 or -2 to 2. And with a scale of 1, and -2 to 2 with a scale of 1. So you can see the graph. Of course, it's undefined at 0. The graph will not show that, of course. But we know it's undefined at 0 because the denominator is x. But if you zoom in, so can you tell me what is the limit from sine x over x as x approaches 0 from either side?
+1.
Correct. And we don't care whether it's defined at 0 or not. We know that it's not the same concept. But if you want to zoom in, and that's 2. Okay, it doesn't do it exactly what I wanted it to do. I wanted to move this to 1.5. You will see the little blip right here. Almost you see it. Almost. I don't understand why the zoom in doesn't work. It takes me in other places. It should zoom in. It doesn't help me, but I just wanted to show you, and you don't have to look at the graph. Okay, now it's here. Okay, it doesn't matter. So we can just plug it in. If we plug in 0, it will definitely say error. We knew that. Okay, so back to the book. There is nothing else I wanted to say here. This is all done, unless you have any questions. Find the horizontal and vertical asymptotes of each curve. So let's choose an example and then move on. Okay, I'll choose one, let's say 47, a simple one. We don't have to factor. All the other ones need to be factored and so on and so forth. So y equals 5 plus 4x divided by x plus 3. So in this question, we are asked to find vertical, horizontal asymptotes, but I'm going to add and corresponding limits. Just saying, oh, I know this x equals 3, -3 is a vertical asymptote is not good enough. We have to determine the limits. Okay, so let's start with the vertical asymptotes. So can anyone tell us which is the vertical asymptote of this function?
-3.
Yes, of course, because x cannot be -3. So we know that this is a vertical asymptote, but we also have to determine the limit as x approaches -3 from the left and the limit as x approaches 3 from the right. Of course, -3 from the right of the function. 5 plus 4x, x plus 3, x plus 3, 5 plus 4x. Let's identify the sign of the numerator and the sign of the denominator, because whatever this is, it's over 0. We know that. Otherwise, it would not be a vertical asymptote. So 4 times -3 is -12. -12 plus 5 is negative. So both tops are negative. -3 from the left, what is the sign?
Negative.
Yes. So then this has to be positive infinity. -3 from the right, which means -2.9.
Positive.
Yes. So then this must be negative infinity. Of course, the limit from either side does not exist. So this is, these go together. Once I say vertical asymptote, I have to show the limits. So this is finished with vertical. But now I have to discuss horizontal. For the horizontal, what limits do I need to determine? Since this is a rational function, there is no need to determine both, because they will be the same. But this is not the case always. This is true, they are the same for rational functions, for pure rational functions, no combinations with other functions. So what will be the limit as x approaches infinity from 5 plus 4x divided by x plus 3? Like we did before. What is the degree of, obviously the top goes to infinity and the denominator goes to infinity. So what is the degree of the top? Do not drop the limit operator, please. What is the degree of the top?
One.
Yes, so I have to factor out x. The same thing with the denominator. So now can anyone give us what is missing here for this to work?
5 over x plus 4.
Excellent. And of course, you're going to say 1 plus 3 over x. Good. This was the whole thing, the whole purpose. Where is 5 over x going? Where is 3 over x going? And now I can drop the limit operator because I applied it. I applied the tendency.
Zero.
Yes, so then the limit will be?
4.
Excellent. It's a pure rational function. I don't have to determine this one. It will be redundant. It will be the same. So then y equals 4, horizontal asymptote. Full stop. Okay, any questions?